Okay. So our lecture today is titled Application of Machine Learning in Power System Asset Assessment. And this lecture is intended to be like an introduction to this important topic. It's a hot topic, how we can apply machine learning in different applications, including assessment of our system assets. These two pictures are actually for two of my students. One of them, this is using an RF antenna, and he's trying to measure partial discharge of a ceramic insulators. This project was conducted with Kinetrix. And this is one of my students using acoustic sensors here attached to the tank of a power transformer. And again, he was trying to see if there's any partial discharge inside the transformer. Now, this lecture is based on two components, machine learning and power system assets. So we need to have a sort of introduction about the two topics. What do we mean by power system assets? And in the context of this seminar or this lecture, what exactly we are looking for. And then the second thing, we're trying to work on machine learning introduction without going into details. As you know, this is a huge topic, machine learning, and the intention here is not to cover all the aspects of this topic, but rather to cover the general idea and then the application of this. So I will be giving two examples some of the examples will be related to outdoor insulators. In outdoor insulators, we will check first, we will talk about them briefly, what are their problems, and then we will try to use machine learning with detection techniques to discover those problems, and then we'll talk about transformers the same way. And then I will end up my lecture by highlighting some of the future trends where this line of research is going. So to start with the power system asset, this is a schematic showing a power system from the generation station where we generate the power here. Then we have the power transformer to step up the voltage. Then we have the overhead lines, transmission level, and then we have the transmission substations will start to reduce the voltage level at different steps until we reach to the small transformers that they are just connecting outside the houses to feed the loads. Now, these assets are different. There are generators, transformers, overhead line insulators. There are circuit breakers, although not shown here. There are sometimes underground cables as well. Now, all these assets, the main factor that decide their life is the insulation system. So most of the assets will fail not because of the failures of, for example, in transformer, failure of the copper or the silicon steel inside the transformer, but because of the failure of the insulation system inside the transformer. So we need to understand what are the different insulation systems and where they are used. So there are basically three different types of insulation systems. The first one is the gas. The gas material, we have it in the form of air. Air is an insulation by itself, and insulation in a sense that it does not allow the electricity to pass through it. It works as an electrical insulation. For example, if you go beneath an overhead lines, there is no current will go through your body. Why? Because between you and the overhead lines that is energized, there is air, and air is an electrical insulation. So this is the most natural form of gases that we use in our insulation systems. There is the SF6. SF6 is a special material that we use in our insulation system. So this is the SF6. SF6 is called an electronegative gas, and it has a certain ability to absorb electrons. Once it absorbs the electrons, it still stays as a stable material. If you remember from chemistry, once an atom that is absorbing an electron, it goes through what we call an excited state, and it stays excited until it releases the electron. So it becomes unstable material. However, SF6 has the ability to absorb electrons and still stays as a stable material. Now, how does this help us? Because when you, for example, open a circuit breaker, there will be an arc. So the arc is composed of electrons. So SF6 gas will absorb these electrons and then will quench the arc. So this is a GIS system, gas insulator substations. These are, there is a bus bar inside. We don't see it. There is high voltage bus bars. This is a 400 kilovolt Merlin Geron. This is a French company. And inside these tubes is SF6 is used as a gas here. And why we use this? Because if I use air, I need to have a much bigger distance between, this is the three phases, phase 1, 2, and 3. So they are very close to each other. So this will make the design of the substation very, very compact. Okay. The third form is vacuum. And this is used for relatively low voltages, not for a very high voltage. We use vacuum as an insulation material. Liquid is also used, and liquid is used in nowadays these are the most three common use. The first one is the most common application, which is mineral oil. It's a hydrocarbon oil. We use it inside transformers, especially distribution transformers or open power transformers. We use it inside circuit breakers. So this is the cheapest and this is the most common use of liquid. But also we use silicon oil. Silicon oil is relatively, when it comes to the cost, is more expensive than mineral oil. But it has an advantage. That is the fire point, or the point at which the oil will explode, is much higher than mineral oil. So silicon oil is used in transformers where the hazard of fire is very critical, like schools, high-rise buildings, or hospitals. So we use silicon-filled transformer, or sometimes we use what we call dry type transformer, which doesn't have any liquid, dry type transformer. Okay, so this is, we use it especially for those places. So either silicon-filled oil or dry type transformers are much more expensive than mineral oil. And finally, and this is the new trend, is to use ester oil. I mean, oil coming from vegetables. It has certain advantages. People thinking that oil will, at certain day, because this is coming from the crude oil, so this might vanish at a certain time. It will vanish actually. No one knows when, but this will happen. So we need to have alternatives. Plus, the degradation of this in nature is very bad. Those are much better degradable materials. So this is more friendly used materials as well. So this is the second form of insulation, is the liquid. The third form, which is the solid. And the solid comes in different forms. For example, this is an outdoor insulators. This is the high voltage here. This is the high voltage, and here is the ground. So between the high voltage and the ground, this is the insulation. Here is the insulation as well. So this is made from ceramic materials. Okay. This is bushing. This is called outdoor insulators. These are bushings where you have the high voltage from the top. So this is the high voltage here coming from the top. And here it is the structure, this is in the ground. This is at the entrance of the SF6 substation I showed you in the previous two slides. This is underground cable. We use here XLBE material, XLBE, which is crossed polyethylene material. So it is a rubber material used here. This is the high voltage, and this is the ground, and this is the basic insulating material here. This is a cutout of a transformer that shows the paper insulation. This is a cellulose paper. You can see here between each layer there is a cellulose paper, and there is also press boards. Here is at the bottom, if you see, this is a press board, and this is some press board here between the high voltage and the low voltage. So these are the main three forms of insulation that you can see in the power system components. Now let's move to the second part. So this is an introduction about the insulation that we want to monitor. Now let's have an introduction about the machine learning, and then we'll have the specific examples. Now the machine learning process, it goes through different stages from collecting certain data. So we have to use sensors to pre-processing this data, extracting some features from this data that help us to distinguish between the different problems. Then sometimes these features are huge in number, so we need to select the most important features, and then we use that classification to reach to a decision. So let's start with collecting the data. Before you collect data, you have to ask yourself certain questions. The first one, what is the insulation system of interest? Are you monitoring a transformer? Are you monitoring an outdoor insulator, a circuit breaker, a cable? So it's very important to understand the insulation system, and it's very important to understand the physics of that specific insulation system so that you know exactly what you want to measure. And this will take us to the second point. What I want to measure? Do I want to measure a current? Do I want to measure partial discharge? Do I want to measure anything else in that? So this is also depends on the physical phenomena I am measuring. So it's very important to understand the physics of the insulation system, their aging mechanism, so that I will be able to monitor it and try to detect any defect in those insulation before they propagate and lead to a complete failure of the equipment. What are the sensors I want to use? Now, you will see that for the same phenomena, we can use different types of sensors. So which sensor is good for me? Which is the sensor or sensors I would like to use to measure that specific phenomena? And what is the objective of my monitoring system? What exactly I want to do? Do I want to have a record? Do I want to have to come up with the decision? And so on and so forth. So in a very simple language, collecting the data is composed of three major components. The first one is the sensor. That is a sensor in a very crude or a very simple way. It's a device that converts physical phenomena into electrical phenomena. So here there is something physically I am measuring. Could be electrical, could be non-electrical. For example, an ultrasonic sensor, it will convert an ultrasonic sound or the pressure that comes from the ultrasonic waves. So this is the physical phenomena. This is my input into a voltage. Now, in most of the time, especially in the context of our application, we always convert everything into a voltage here. So the output of the sensor is a voltage regardless what I am measuring here. Okay. Now, when I measure this voltage, I need what we call this is a conditioning circuit. Conditioning circuit. I need to do some certain conditioning. Now, this conditioning could be an amplification. I need to amplify the signal because its value is extremely small that I cannot measure it. Sometimes I need to filter. Okay, and this will be also discussed in the coming slide. Once I have the signal conditioned properly, then I have to show it. Then I have to have the measuring system. This could be a scope, for example, could be a voltmeter, could be anything, any device that show me the output of my voltage that comes out of my sensor. There are certain important things when I select these, the sensor, the amplifier, the measuring system is the frequency matching between all these components. Meaning, for example, I'd like to use a sensor, an ultrasonic sensor, to measure what? I want to measure partial discharge. What is the frequency range? Let's say the frequency range is from 20 to 80 kilohertz. So I know that this is the range of my sensor. Then my amplifier, my filter has to work exactly on the same or a bit higher or a bit smaller range. I cannot have an amplifier that is used to amplify signal in, for example, from DC to 10 kilohertz. Okay? If I use such an amplifier, it will not do any good for me. So I have to make sure that my amplifier is good in that specific range. Now, if my sensor, on the other hand, is an RF antenna, then my range of frequency will not be in the kilohertz. It will be like from 400 megahertz into few gigahertz, 2 gigahertz. This is much higher frequency range. Then my amplifier, if I use the same amplifier I use for the acoustic signal, I will not be able to amplify the signal. So this matching is extremely important between the amplifier and the filter and the sensor. And then the measuring device, and I will show you when there is a mismatch or when the device has certain limitation, I will not be able to see clearly the signal. So this is an example here. Here, this is example, I'm using an RF antenna. So I'm using an RF antenna to measure partial discharge from insulators. Okay. Now, I used two different types of oscilloscopes. The first one, which is this one, the bandwidth of the oscilloscope is 60 megahertz. This one, the bandwidth is 2 gigahertz. So they are two different, although the sensor, the input signal, the output amplifier, all of them are the same thing. Okay, but the only problem is in the measuring device. So when you look here in this range, this is 60 megahertz. So the signal, this is like, now this becomes like 500 megahertz. Okay, with 0.5 gigahertz. So you see here the signal is around few, or maybe 100 to 200 megahertz. Sorry, 100 to 200 megahertz. There is something here, but then nothing at all. Why? Because the measurement system that I have has this limited bandwidth, so I can only see things. Although the phenomena, I'm using an RF antenna that can measure things in the gigahertz, but I cannot see it. Why? Because of the mismatch in my oscilloscope. On the other hand, this is a much better oscilloscope, and you can see here, this is actually the 500 megahertz here, it's around here. Okay, see most of the information is in the gigahertz. This is 1.52. So there is a lot of things are missing from here. We don't see it. Why? Because again, the oscilloscope was not good. Now, another important thing is when you select your sensor. For example, these two sensors are both ultrasonic sensors. The first one works in a range. This one is from 20 to 80 kilohertz. Now, this is just at the border of the ultrasonic. Okay, as a human being, we can hear from 0 to 20 kilohertz. Anything higher than that, we cannot hear. But of course, that's not really, I mean, like a sharp cut. Of course, we can hear a little bit here above this. But the other sensor, the bandwidth is 100 to 450 kilohertz. This is deep in the ultrasonic range. So we want to see what is the response of the sensor when it comes to noise. We compare them. So we see this sensor, see here the volt. Again, as I mentioned, the sensor output always in volt. So here, this is up to 20 millivolt. This is 0.02 volt, which is like 20 millivolt. This one, 2.5 to minus 3, so this is 2.5 millivolt, much less. So this is like a very small noise, but this one you see here, big spikes. What does this mean? It means that this sensor can pick the noise, but this sensor is immune to noise. What we did here, we just brought a motor and we ran the motor beside the sensor, these two sensors. So this one was very immune from the noise, but it is very sensitive to the partial discharge in that ultrasonic range. So selecting the sensor sometimes is very important because I want to have my sensor immune from the surrounding noise. However, I want it to be very sensitive to the phenomena I am measuring. Now, this is enough about the sensor. Let's move to the pre-processing. I selected my sensor, my amplifier, my filter, my device. Now I'm collecting data. Okay. Now this data still will come with noise. This is an example of partial discharge. This is a partial discharge. We measure it using a high frequency current transformer in the lab. Okay, so this is the original signal. Okay, and it was measured at a controlled sample at certain voltage, 13 kilovolt. But when you look to this signal, you really don't know is this is a noise or this is a partial discharge. So we have to apply some denoising, which we call it pre-processing. When we apply something called wavelet, this is an advanced technique to remove the noise. We get something like this, and now we can see the peak. This is the peak of the partial discharge. Small value, yes, but it's much better than this. This is like we don't know what is going on here, but this one, this is the estimated beta. We say estimated because we denoise it and we come up with the sort of estimation of the original signal without the noise. So pre-processing is extremely important. If we don't pre-process the signals, we will have a lot of noise and we cannot extract anything useful from this. This is another example for acoustic signal. Okay, this is acoustic signals with a lot of noise. Okay, and then here after denoising it, we see here a very clear signal that we can extract some good information from it. Also, we work with images. Images is now become extremely important in the condition monitoring, especially for outdoor insulators, and I will talk about some examples. So this is an original image. We took it for the surface of ceramic tiles covered with silicone rubber material. Okay, now this is the original signal, so which is we call it here two-dimensional signal. The signals that I showed you partial discharge called one-dimensional signal because you have only the x-axis, the t. Here, this has an x and y. We call it two-dimensional signal. So if we look here, the first thing we want to do here is trying to crop this and resizing it so it becomes much better. Those tiny dots is water droplet, and I will talk about this problem specifically in the coming slides. And then, okay, it's not very, I want to see, actually, the objective here, I want to see a contrast between the water droplet and the surface, because I want to quantify something on those water droplets. So then I will do here some, I will do some pre-processing, sharpening the contrast level, adjusted between the water droplets. So we see here, becomes clearer to me. And then I will use denoising and gray level threshold. So it is either black or white. So when you look here, it is much better. I can here clearly identify the water droplet on the insulator surface. So this is what is meant by pre-processing. Now I have an image or a signal, call it 1D or 2D signal. Now I'd like to extract features because at the end of the day, I want to come to certain decision. Those signals and their pre-processed signals that comes out of them, I want to feed them to an artificial intelligence system. But I can't feed them as a raw data. I need to select some features from them. I need to select some important information from them so that I will use this information as my input for the machine learning system. And there are basically the main two categories of features can be classified as statistical features. What is the statistical features? For example, you are measuring a peak of a partial discharge, a value, a number. So you will have a lot of data, 1, 2, 3, etc. So you take all of this data and you draw for it its distribution. So you will have an average, you have standard deviation values. So these are all statistical features: the average, the mean value, the standard deviation, the kurtosis of the data. The kurtosis is how sharp or how wide is your information. So instead of entering all of this data, I can extract from it the mean. This could be like maybe a vector of 1,000 points. This is my original data after pre-processing. Remember, for example, if this I have here a signal like this, this is digital signal, means it is composed of points. Okay, so one signal maybe has 1,000 points. So I can extract from this 1,000 point the mean, the standard deviation, the kurtosis, which is how this is just a number that represent how narrow or wide is my distribution, and maybe the skewness, which is sk, which is if the data is skewed to the left or skewed to the right or not skewed at all. So I will extract few of those features that will represent all of this. So this is my input feature. Okay, instead of entering the whole thing, which is a huge vector, I will just select some statistical features. In some cases, that is enough. And those features, when we have distinct signals, will be enough to represent the phenomena that you are measuring, and I don't need to do more. But in many cases, no, you need to have spectral features. Spectral features, which is the frequency content of your signal. Your signal, if it is, for example, in time domain, for the partial discharge. So maybe you need to have the discrete Fourier transform. So you extract the frequency. This is one of the signals that we have, and this is the frequency content of that specific signal. So we can select the features. Now you can see there are many components. Okay, maybe you can have like 500 or 1,000 or maybe even more of frequency components, which will take us to something very, very important when it comes to selection of the features. Or we can use the wavelet transform. A wavelet transform, for those who don't know, it is a time frequency transformation. In the frequency domain here, we don't have any time information. The time signal will be, the time information will be completely lost here because the x-axis is only frequency. There is no time information. We don't know this peak happened at what time. Okay, but in the wavelet transform, we have both the time and the frequency. So these are different frequency bands at different times. Okay, so we can capture both. I mean, the scope of this course is not to go in details here, but this will also take us to different frequency bands. Sometimes we go and take each single frequency band and then calculate to it the statistical features we had before, like the kurtosis, the skewness, sometimes the energy available in these frequency bands. So we extract some more information from these bands. Now, but as I mentioned here, many times we end up having a very, very long feature vector, a lot of information. And this is what is known in machine learning the curse of dimensionality. That is too much for me. I don't want to have all of this information. I want to reduce this information. And yet I want to get something valuable from this information. I want to get something that is really representing the phenomena that I am measuring. So I need to do what we call feature selection. Okay, I want to reduce the feature, and there are several techniques. One of, again, I will not go here in details because each thing here is, I mean, we spend hours talking about it, but here the objective is to just highlight some the big picture, the whole picture, and then whoever is interested, he or she can go and dig deeper. So there's something called the stepwise regression. In this stepwise regression, you will select your feature based on their statistical significance. There is a measure that we do, and based on they call it the partial F statistics. This measure will tell me if this feature is important or not important. Another one is something called the principal component analysis. This is the PCA. This is a very famous technique used for reducing the features. It has certain advantages, disadvantages as opposed to the previous one, but this is one of the common techniques that we use, and you will see I will use both of them in my research as we move on. Okay, now we come to the last stage. I have measured my signal. I have cleaned it from noise. I have selected the most important feature, and now I want to do the classification. I want to classify. Now, the classification is done using two different techniques, one of them called supervised learning and unsupervised learning. For those who don't know, if I do a supervised learning, it means my data is labeled. What does this mean? Let me assume that I am measuring, let's say, a phenomena using an RF antenna. Let me just give a simple example. And I'm measuring here uh, from an insulator, measuring two things, measuring discharge from the insulator and discharge from the hardware. Okay, so I will call this is PD1 or PD, and this is corona. So I'm getting here signals. I know now in supervised learning, so what we do here, basically I initiate the condition to produce PD1, and then I will have, this is my PD, partial discharge, then I will have signal 1, signal 2, signal 3, maybe 500 signals under PD, okay? And then I will have another 500 signals under corona. 1, 2, 3. So my data, this data, and this data called labeled data, means this data is labeled to partial discharge, and this data is labeled to corona. So this is we call two-class problem. Okay. So then what I will do a measurement that is not here, a new measurement, and then my system should tell me if this is a PD or it is a corona. Okay. So this is called supervised learning. Now, in supervised learning, there are two different types of supervised learning. The one is called classification. In classification, we classify the defect into something discrete, like, for example, PD, like corona, like crack. Okay, so it is classes that we are trying to do. Maybe sometimes we use the word high, medium, low, so it's just classes. On the other hand, we use the supervised learning not for classification, but for regression. In regression, you find a value. So instead of tell me these are two classes, I want to predict the value of the partial discharge, not just the class of the partial discharge, but its number, its value. So this is like a continuous function. This is a discrete function. Now, in this lecture, I will talk about supervised and classification. Now, unsupervised learning is a different story. In unsupervised learning, I don't have labeled data. I just collect data. Okay, and then these data will be like clustered, different classes. I don't know what are those clusters, but they are different clusters. Then I can do something about each one. I can predict what each cluster. But here I will segregate the data, not based on something I already know in advance called labeled data, but this is unlabeled data. Most of the applications in high voltage electrical insulation diagnostic is a supervised, either classification or regression. Unsupervised, there are some applications, very limited. I never worked in any of them myself. So I will just talk about these two. Now, when we come to the classification, here becomes the machine learning system. And here there are tons of machine learning systems. ANN, artificial neural network, subword vector machine, k-nearest, polynomial classifier, and there are many other classifiers, all of them under what we call machine learning algorithms. Okay, in very brief, for example, this is the topology of the artificial neural network. What is this? This is the input feature. This is the data that I'm extracting from the signals. This is the one that I told you could be the statistical features, could be the spectral features after the reduction. So I enter these ones, and here is my output, the label that I use. So in any machine learning algorithm, what we have two stages: stage of learning and stage of testing. In learning, what I do, let's say I have, back to my problem, I have partial discharge problem where I have signals 1, 2, until 500. So I have 500 signals, all of them, I collect them when there is a partial discharge on the surface. And also I have a corona. A corona is a discharge not on the surface, but on the hardware, in the conductor itself. So again, I have 1, 2, until 500. I also have 500 signals. Okay, so let's say I will take 60-70% of this data, and I will train it using this. Now, these are some constants, input layer, the hidden layer, that is will adjust. So what I will do, I will tell the machine learning here, which is the ANN. Okay, for the signal number 1, this is my input, it's a PD. Signal number 2, it's a BD. Signal number 3, it's a BD, so on and so forth until maybe I will reach up to 400. So what it does here, it will try to adjust these constants, okay, so that it will map this to this. Okay. Now, after I train it, and there are parameters to know that I'm training, then I will go and train it for the other feature, which is the corona. Okay, this signal is corona. This is corona. So I will train it for both PD and corona. Then I will leave like around 100 signals not touched, not used in the training, and I use it in the testing. I will come and bring this 100, and I will see, will the system be able to recognize those 100 signals? And then I will tell, okay, how good or how bad is my classification accuracy. Okay, so that is the whole idea of machine learning. Support vector machine, it works in a different way. For example, if I have the partial discharge and the corona, 2 class problems. So basically, what it does, it put them like this in a plane and separate them by a hyperplane. Okay, so this is the data, for example, in partial discharge. Okay, and this is the data used for corona. So the data will be segregated, and we'll try to maximize the distance between the 2 classes. Okay, so we use the last points in this class, and I draw a line here, and the last point from this class, and I draw another line. So this is the margin. Then when a point comes, I will classify it either for PD or corona. It is in this cluster or in that cluster. If it is in the margin, is it closer to this or to that? Then I will come up with a probability. This is like 80% it's a partial discharge, 20% it's a corona, and so on and so forth. Again, this is called KNN or K nearest neighbor. Again, here the same thing. We will have the data here. Let's say here the blue one is the partial discharge, and the red one is the corona. Okay, and then I have a new data. This is I don't know. So I will see, is it closer to the partial discharge or it's closer to the corona? Okay, so there is something called KNN1, meaning that I will see the distance between this point and only the closest point from the corona and the closest point from the partial discharge, and see the closest one. Then this is KNN, let's say 3. So what I will do, I will take the distance between this, and this, the 3 closest points to it, and then I will take this, and this, and then I'll take the absolute value of these vectors, their magnitude, and I see this one belong to this or to this. Sometimes if you KN1, maybe it will belong to corona. If you take 3 vectors, KN3, it will belong to the other one, and so on and so forth. The last one I'd like to okay, there is one question here. Let me see. Can you please explain KN11 and KNN3 again? Okay, I will do that. The question is, can you explain? KN1, KNN, K nearest neighbor. When I have the classes here, so this, as I said, this is the partial discharge, the blue, and the red triangle is the corona. And I have my point. If I use KN11, means KNN1, meaning what? I will take the distance between this new information or the new data point that I don't know, and I will take the distance between this and the nearest one from corona, and see the distance. Let's say the distance is X. And then I will take the nearest distance between this and the blue line, which is this one. This may be 3x. So this is closest to this one. So it is, I will say this is corona. In KNN3, I will take the distance between the new data point and the closest, the three closest points to it, which is this one, and maybe this one, or that maybe this one is closest actually, not this one. Okay, and I will take the distance. Maybe this is x, 2x, and this is 5x. So total of 8x. Now this will take the distance between this one and the closest three from the other class. So this is 3x, or maybe this is 2x actually. This is 3x, and this is maybe 4x. So we add them and see this one is the closest to those three or to those three, the distance. And this KNN5. Okay, so as I said, in many cases you will find that maybe this is better, and in my experience I use more of KNN3. This is the one that is, I found it with experience, this is the best one. And it's very important to understand one thing about machine learning. There is no single algorithm that is good for everything. It is based on the nature of the data. You will find that in certain data KNN works excellent. In certain data, ANN is the best. In certain data, VM is the best. And vice versa. You will find KNN do very poorly in this type of data. So the machine learning is actually, it is a science and an art. You have to have the common sense, and you have to do a lot of working with it, because the whole process, as you can see from the beginning until now, from selecting the sensor, from collecting the data, pre-processing the data, extracting the feature, there is a lot of effort has to be done there until you reach to something that is representative and a stable machine learning algorithm. The last one, this is called polynomial. In the polynomial here, this is my input feature. Okay, that this is the training vector x. Okay, and this is the target sequence. So this is, as you remember, this is a label data. So this is x1, x2, x3. So this is the feature vector, and this is the target that I want to predict. So this is the output, and this is the input. Okay, and then we'll try to find a combination of those higher order polynomial that I can match those vectors to this. So for example, I will have something like this is x's, for example, a0 plus a1x plus x1 plus a2 x1 x2. It's a non-linear, so this is multiplication, plus a3 x3 cube plus etc. Okay, so you can see here this x, this will be like x1, x2, etc. So this is the feature vector. So we'll try to find a multiplication, try to find summation, etc. between these values until I match this to that, and then I will bring my test feature that I never used in the training process, and then I will use this to test and see how good or bad is my output feature. That's enough for as an introduction to machine learning. Let's talk now about outdoor insulators. So, okay, now I will talk about very specific applications. The first one is outdoor insulators. So here, this is an overhead lines. And overhead lines, we have an insulators that hold the high voltage from the grounded tower. It is very important type. So these are the insulators, of course. These are the insulators that holds the high voltage from the grounded tower. This is ground. Okay. Now they have to withstand steady state electrical stress. They have to. There is high voltage, so they have to hold this high voltage. Okay, I don't know why it's going automatic now. Then they have to work with transient voltage from switching or lightning. They have to work mechanical loads, and it has to do all of this under severe environmental conditions. There are two main types of outdoor insulators. There is ceramic and there is non-ceramic insulators. Ceramic is glass and porcelain. Non-ceramic mainly made from rubber, silicone, rubber material. Okay. Now each one has an advantage and disadvantages. Ceramic we have very long history of use, more than 100 years. Very stable material. So if there's an arc on the surface, this is a glass insulators, but it could be also ceramic. It is very stable material. On the other hand, they have certain disadvantages. They are heavyweight. You can imagine that, which will lead to a very strong mechanical structure, which is the tower to hold them. Then they have a very bad thing we call the poor contamination performance. When the surface is wetted, there will be a leakage current on the surface leading to a flashover. So the pollution performance is extremely bad. On the other hand, silicone rubber, which is invented like 30 years ago or 40 years ago, has certain advantages. They are lighter in weight, so the structure will be much easier to do. Vandalism resistance, this is rubber, and inside this is a core from fiberglass. So this one is, if they fall in the ground, they break. This is vandalism resistance, and they have a much better performance in the contamination. I will talk about that later on. They have certain disadvantages because of the aging. They are susceptible to aging. We don't know their long-term performance yet compared to this, because this technology will have long history, and it's very hard to detect if there is a fault, if there is a crack internally. In the fiberglass, I cannot see it, but this one, if there is a crack here, I can see it. Okay, so here I want to start with ceramic insulators. So I will talk about two different problems. The first one, detection of physical damage using RF antenna and ultrasonic sensor. So we'll see how we can do that. And the second problem that I will talk about is how to evaluate the pollution severity. How severe is the pollution? And we will use a camera. So here we'll talk about three sensors: RF antenna, ultrasonic sensor, and regular camera. These are two different problems. Here I am concentrating on detecting physical damage. Here is I want to quantify the pollution severity on the insulator surface. And this is for ceramic insulators because these are the major problems here. It's the poor contamination performance, and also they are not vandalism resistant. They might be cracked, especially for ceramic insulators. Now, as a sort of introduction, the age of ceramic insulators is extremely old, those ones, okay? We have in North America around 150 million of those ceramic insulators that many of them, they exceeded their life, okay? Which is 30, 40, 50 years, okay? Now, although the cost of those insulators is 5 to 8% of the overhead line cost, they are responsible for 60 to 70% of the line fault. Okay, so most of the cost doesn't come into this material. However, most of the failure come from those materials. So it's very important to inspect them. Now, what is happening in ceramic insulators? There are different problems because of their aging. One of them is a crack, internal crack, or external crack, because this is like made from cement. There is a cement material inside, and this porcelain. So this cement will try to expand and contract because of the difference in the temperature between summer and winter, between day and night. With years of service, a crack starts to develop. Once we have an internal crack, then you start to have partial discharge inside. And this partial discharge gradually will lead to complete failure of the insulator. So here we have these insulators. There are some of the problems. As I said, there is a surface crack here. We did that crack deliberately, we want to see, and we did a void. There is an internal void here. So we have a broken insulator as well. Here, this is a damaged, broken insulator. And also we have the crack insulator, we have the hole, we have the broken insulators, and we have a corona noise. Now, when you have a high voltage line, there is something called corona. A corona is a discharge around the conductor. So because of the high voltage here on the conductor, this is a very high voltage, what is happening? The air around will start to move from an insulating material, as we mentioned before, into what we call as plasma. Plasma is the fourth state of the matter, plasma. Okay. Now, plasma is nothing but conducting gases. Okay. So here we'll start to hear a sound like a zzz. This sound is the sound of the breakage of the air molecules and become more and more conductive. This is one slide that shows to you our research here. So let's start from here. This is our sample. Remember, let's go back to what we said about the measurement. First, you need to understand your insulation system. This is my insulation system. What I'm measuring is the outdoor insulators, and here we have different defects. So these are insulators. You have 1, 2, 3, 4. This is called cap and pin. So they are connected in series. Here is the high voltage here, and here is the ground. Okay. So this is the insulation system. Now, the sensors, we have two different studies. Actually, they were conducted by two different master students. The first one using the RF antenna. So this is the RF antenna that they use. The other student use an acoustic sensor. Both of them, more or less, they are measuring the same thing. They're trying to detect the defects on those insulators. Okay, so this is the selection of the sensor. Now, understanding this, I'm not showing it here because of the space, but we have to have an amplifier. This one has an internal amplifier. This is a commercial sensor. It's Japanese made, and this is a Chinese antenna. And this one, we connect to it an RF amplifier. And then this one, because the RF antenna is having a very high frequency, we connect to it another scope. So you can see here, this is an antenna plus an amplifier plus a scope. So you can see clearly that this system is way more expensive than this system, which is just a sensor that can save the data inside. Now, let's move now to the second point, which is the data itself. So this is a typical RF signal measured from the oscilloscope, and this is the time. It is in nanoseconds, so it is a very high frequency. On the other hand, the acoustic sensor, it does something here very interesting. Although the signal is a relatively higher frequency than what you can see here, this is a very low frequency signal. This sensor, it does do some pre-processing internally, which is the following. It takes the envelope of the signal. So if I have a signal like this, let's say this is very high frequency, what it does, it comes here and takes the envelope of the signal, so it converted to a very low frequency. And if you took here and see the f of t here, and this is the feature, you will see that this is our very low frequency. It's like 60 hertz, because the signal has been converted from a high frequency into an envelope of the signal, which is a very low frequency. And you can see we have only three features: the 60, the 120, and 180. However, here there are many features, many points. So we use something called the wavelet packet, which is similar to the wavelet transform. We're trying to take certain bands and finding the energy of those bands. And then, so this is my feature. I select my feature, and then I come and we use A and N in both studies, artificial neural network, and trying to find the defect type. So this is some more information about each sensor. So this is the commercial name of the sensor. It has a band, has a center frequency at 40 kilohertz, which is ultrasonic and work in that range, the ultrasonic range. But the output is not in the ultrasonic. The output is a pre-processed. So the features are the 60, the 120, and the 180 hertz. And the problem we want to detect corona, crack in the insulator, and surface discharge due to pollution, means dry band arcing. There's no time to go through this, but if I have the insulators and we have pollution here, we'll start to have an arc on the surface of the insulator if we have pollution. On the other hand, the antenna has a bandwidth between 1 to 2 gigahertz. This is the pass band, and it has certain gain, 14 to 18 dB. We use the entropy, energy, kurtosis, skewness of the wavelet packet, as I mentioned before. And here we detect corona, crack, and hole in the insulator. In the ultrasonic, we do not try to solve this problem. Why? Because the hole inside the insulator, the signal that comes out of it, the ultrasonic will die off. It is very hard to measure it. And this is one of the disadvantage of using the ultrasonic sensor. On the other hand, here, we did not try to measure the dry band or the surface discharge because of pollution, because this is a low frequency phenomena. It does not produce signals in the gigahertz. So the RF antenna, and we tried that, cannot detect anything. And this is one of the drawbacks in the RF antenna. So it's very important to understand the limitation of these sensors. No perfect solution for all of the sensors. So this is just a rough, this is some of the results using the RF antenna that the three classes I just mentioned. We have extremely classification accuracy. Classification accuracy, it counts how many classes correctly classified as opposed to the total classes. So if I have 100 cases, 96 cases were correctly classified, 4 cases only were not classified. So each class is having a very high, this is the average. So we did that a couple of times, and this is the maximum. Again, you can see here, it's very consistent, very high classification using the RF antenna. When we use the ultrasonic sensor, here this is I'm trying to show you the clusters of the three classes, which is the corona, and the cracked porcelain insulator, and the discharge from a contaminated surface. Okay, so this are the three classes. Now you see here, these two are overlapping. The discharge from a crack and the discharge from a contaminated. The features are somehow overlapping, and this will lead, you will see here the classification accuracy for these two are relatively lower. The corona is 100%. Why? Because there's a huge distance between this class or this cluster and the other two clusters. The other cluster, there is some area of overlap, then why we have here a low classification accuracy. Now, we did a lot of work after that to improve this by changing the classifiers, etc., and we get a better results, but that's not the place to discuss these results. If you are interested, I can send you the papers. I mean, everything, by the way, I'm mentioning today, all the results is the research of my students. So if there is something specifically that you like to get, I have, the papers are, most of them are available in the IEEE Explorer. If you can't find it, I can send it to you. Okay, so this is the last thing before the break, then we go for a break. Now here we're trying to, this is again ceramic insulators. Now we want to evaluate the pollution severity. Now, this is a ceramic insulators or glass insulators. It's a glass. Still, as I said, ceramic contains both glass and porcelain. So these are 4 cap and bin insulators. This is the high voltage here. And here's the ground, as usually this is the configuration. These are polluted insulators, and because of the pollution and if there's humidity, this pollution will start to dissolve. You start to have a current on the surface. This is what I called in the previous lecture, in the previous slide, the dry band arcing or the surface discharge due to pollution. And then this will start to propagate eventually until we have a flashover. A flashover is an arc from the high voltage to the ground, and this will trigger the circuit breaker to interrupt. Now, sometimes you might have a recloser. The recloser, basically, it will open and close a couple of times. If you are this is most of the time in overhead lines. Whenever something like this happens, it's temporary. Means that once there's a flashover, this flashover will wipe out all the insulation, all the pollution. So it comes again clean. So in many cases, this is not sustainable. So it happens once or twice, and then it removes itself. This is why we use a reclosure. The reclosure is open, close and open and close automatically, so that if the fault is not permanent, it will clear it. So you don't need to permanently open the circuit breaker. Okay, so this is flash over. Now, how this is happening because of the pollution? Now, how we quantify the pollution? We have two measures. One of them we call it the ESDD. The other one is the NSDD. The ESDD, this is a measure for the salt, the amount of dissolvable material in the pollution. Okay, we call it the equivalent salt deposit density. So basically, the pollution that we have in the surface, we want to see how much the amount of salt inside this. On the other hand, the NSDD, it measures not the conductive or the active element, but the inert part, which is the dust, how much dust we have. So these two measures are extremely important so that it will tell us how severe. And based on the severity of the pollution, we select how many insulators we have to have in this specific area, because this is not constant. For example, at certain voltage level, I use 4, but I could use 5 or 6. If I work on a very severe pollution environment, I may need to increase the number of insulators. So how this in the field measure the ESDD and the NSDD? It's very intrusive. Meaning what? Meaning that I need to wash the pollution, I need to collect the pollution, and there is a standard to measure the NSDD in milligram per centimeter square. So here I will talk about only the NSDD because this is the one that we try to estimate using our image processing and artificial intelligence. So basically here you collect, after you clean this with water, you collect all the dust from the insulators, you dry it out, you weight it, and you divide by the surface area of the insulators, the surface area of this insulators. These are given. This is known to us. So it is represented as a milligram per centimeter square. The more we have this, the worse is the environmental condition, and the more precautions we have to be. Now, this is, as you can see, is very intrusive. I cannot go there until I shut down the line. There should be no high voltage here. So you have to cut down the power. You have to go there. Takes a few hours to do all this measurement, take the data, go to the lab and analyze it. So it's very clear that this is not really very practical. We're trying to propose an alternative solution to this problem. And this is summarized in this diagram. Okay, so what we did here, this is a clean ceramic insulators. So, and this is a polluted. You can see here there's the whitish color here. So we try to do bring an insulators. We pollute them using a standard method with a standard pollutant, which is whitish in color. And then we try to have different classes, different pollution level. Okay, and this is the classes that we are trying to predict. Okay, so we have like a clean insulator, and then we have 1, 2, 3 classes of NSDD. So we have it as a range. Let's say from range X to range Y, this is class 1. From Y to Z, this is class 2. From Z to K, this is class 3. And of course, class 0, which is when we have it is clean. Now, we took an image, and then we found that this is the distribution of the total value, which is the pixel intensity from white to dark. And if we take the first pixels, we found this is like an important feature. And this is the mean value of it. Okay, when we draw this, this is the global mean, which is this one, and this area for the first the dark part of the pixels. Okay, so we change this into pixel colors. So when we draw this, we found the following. We found when it's clean, it's very far away from the insulators, the other polluters. So this is like a very clear cluster when it's clean. And here is the pollution level 1, 2, and 3. So as the pollution increases, the color becomes lighter and lighter. So these values will start to change. Okay, and this comes up with our NSDD value. So here, this is the classification. Now, this is like quadratic classifier. This is a special case of the polynomial second order degree. And this is an artificial neural network, the ANN, that we used before. Now, this is what we call the confusing or the confusion table. What is a confusion table? It doesn't just give us the accuracy, but it gives me for every class how accurate was it. So let's see here. This is the testing data only. So I have 24 actually as clean, and they are classified as clean. And then I have 0, 0, 0. So this was a perfect class. When I go to level 2, I have 26 as level 1. However, only 23 classified as level 1 and 3 classified as level 2. So there are 3 classes here are misclassified. When you go to level 2, we have 22 cases, 20 classified. It is level 2 and classified as 2, but there are 1 case classified as 3, which is called misclassification, and 1 classified as level 1, and so on and so forth. But you can see here the accuracy is extremely high, very high accuracy, which is a good start for this to proceed further. Now, this is for non-ceramic insulators. I will stop here. I will stop sharing, and I will stop the recording.